Hey crazies, have you ever noticed how wonky black holes look? Like, why does this thing curve up here? Why does this stick out the bottom? What makes this part brighter and this part dimmer? Why is there a gap here? What is this ring? And where is the actual black hole in this picture? All of those questions can be answered with a little black hole anatomy and some optics. To be as clear as possible, black holes are the blackest black that ever blacked. We can't actually see them. Most of what you're seeing when you look at one is the accretion disk. The accretion disk is what stuff becomes as it begins its descent into the black hole. Accretion is just a fancy word for growth by gradual buildup. In this case, it's the gradual accumulation of matter. Anything that gets close to a black hole is going to get ripped apart and heated. Tidal forces do the ripping, and then friction within the disk does the heating. Up to like 18 million degrees Fahrenheit. This stuff is made of plasma, just like stars. It's that hot. And it's revolving around the black hole at a significant fraction of the speed of light. Fast. Its speed is so high that Einstein's relativity predicts a change in apparent brightness. The part of the accretion disk moving toward us appears brighter, and the part moving away appears dimmer, an effect we call Doppler beaming. Technically, it happens at all speeds, but it's only noticeable near light speed. Fast. And in case you're wondering, we have observed it in an actual image too. It's not just a prediction anymore. But why does it look so wonky? Optics. Optics is the study of the behavior of light, especially how light interacts with matter. The accretion disk is actually flat. It's always in the equatorial plane of the black hole. But when we take pictures of these disks, they don't look flat. Parts of it kind of curve up here, and some of it sticks out the bottom down here. That's just an optical illusion though. The images we see, whether that be with our eyes or with a camera, are made with light. And light doesn't always travel in what we would instinctively consider to be straight lines. You know how when you look into a mirror and it kind of seems like you're looking through a window at a clone of yourself? If light traveled in straight lines at all times, you wouldn't see anything in a mirror. But some of the light scattering off your body hits this reflective surface and bounces. It doesn't really bounce, but you get the idea. Some of that light reflects and enters your eyes, allowing you to see something that isn't in your field of view. You see an image where no object exists. But at least that image looks like you. To get a distortion more like a black hole, you'd have to look into something like a funhouse mirror. Those make the light go in unexpected directions. A similar thing is happening with the light from the accretion disk, except it's not a reflection. Gravity only affects mass though, right? Actually, that's not true. What? Gravity may come from mass, but it affects everything, even light. Gravity is not a force. It's a fundamental change in what straight lines look like. Take these straight lines, for example. With something like a planet or a star, those same lines would look like this. There's only a slight deviation in the path light would take, like a fraction of a degree. Near a black hole, the change is much more dramatic. Paths could easily turn through significant angles. The light being bent by a black hole doesn't have to come from a great distance though. Let's say it came from the accretion disk. The path still bends, and the light is sent off to its destination, our detectors. Those detectors treat the light as though it didn't bend, and they see a distorted image. You know how we can't see the back of Saturn's rings because Saturn is in the way? Well, this is what Saturn's rings would look like with the same distortion. You can see the back. The accretion disk is actually flat, but we don't see it as flat because of the weird optics. Does this make me a flat accretion disker? Moving on. I'm not sure if you've noticed yet, but that accretion disk does not go all the way into the center. There's a limit called the Innermost Stable Circular Orbit, or ISCO for short. Every individual particle in the disk is on a decaying orbit around the black hole, but its orbital speed is helping stave off the fall, so the decay is gradual. That all ends when the particle reaches ISCO. At that point, no speed is fast enough. The particle falls in. Nom 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 nom. That's why we see a gap here. Massive particles can't orbit any closer than this, but massless particles like photons can. Light can orbit a black hole? Yep. There's a special distance where the paths of light turn into circles. That's what we call the photon sphere. Light orbits the black hole at this distance. Of course, if that light were perfectly bound, we wouldn't see it. What we're actually seeing is the light just outside the photon sphere. That light gradually spirals outward until it finally escapes. That's the photon ring found here. So the photon ring is the outer edge of the photon sphere? Well, not quite. Don't forget the optical distortions. And those distortions get more pronounced the closer we get to the black hole. This ring might be made of photons from the photon sphere, but the photon sphere itself is closer in. Again, optics assumes straight lines, so this escaping light appears to come from here. It's just an image of the photon sphere, not the photon sphere itself. Inside the photon ring, we see nothing. That's what we call the black hole's shadow, but it's not really a shadow. A shadow implies something is in the way, blocking the light. That's not what's happening with the black hole. This so-called shadow is just an image of the event horizon. That horizon just happens to be black. If there was some hypothetical skin around that horizon with lights, we would be able to see that. Light coming from that skin would still have its paths bent though. We'd not only be able to see the front of the event horizon, but also the back. But it gets even weirder than that. Some of the light goes around several times. So you'd see the front of the event horizon in the middle of the shadow, and then the back warped around that, and then the front again, and then the back again, and so on, in a set of repeated and increasingly thinner rings filling the shadow space. Physics predicted the size of this shadow. It predicted a gap between the orbits of light and matter. It even predicted what that would ultimately look like from a distance. In appearance, so weird, it's easy to be skeptical. But then we took a picture, and the physics was correct. Our instincts are what's wrong. And until next time, remember, it's okay to be a little crazy. Many of you were wondering how some black holes could be less dense than air. I mean, it's not like there's a lot of them out there. They gotta be really big. Big even for the supermassive kind. But it's because the black hole's diameter is proportional to its mass. You should work it out yourself, it's really fun. Anyway, thanks for watching. Nom 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 nom.